Hi everybody, this is the second video about Fourier analysis. So, Fourier Transform, the first generalization to Fourier series, it allows us to handle non-periodic functions as well. Actually, it's based on interpreting non-periodic functions as periodic functions having a duration of an infinite amount of time. Now, to elaborate the idea, let's have a Fourier series example and see how does the spectrum changes as we approach non-periodic signals. So we have this function f of t. It has a period of 2 seconds from -1 to +1. This pulse starts from -0.5, ends at t equals +0.5. So it has interval of 1 second. These zeros have interval of 0.5 seconds each. Now I'm going to use the complex form of Fourier series to evaluate the spectrum coefficients. So you need to cover this topic before understanding Fourier transform. So C sub n equals to 1 over time integration over time f of t e2 minus j2 pi n f naught t dt. So 1 over t equals to 2 seconds. Integration from -0.5 to +0.5, since f of t have 0 values outside this interval, f of t equals 1 during this interval, times e2 minus j2 pi n f naught. Now, if t is 2 seconds, this means that f naught equals to 0.5 hertz fundamental frequency. So, e2 minus j2 pi n times 0.5 times t dt, which equals to 1 over 2 times 1 over minus j pi n, 0.5 times 2 is 1, and e2 minus j pi n t, from -0.5 to +0.5, which gives us 1 over 2. So e2 minus j pi n over 2 minus e2 plus j pi n over 2 divided by minus j2 gives you sine m pi over 2. And we have this m pi. So this is C sub n. Now let's draw the spectrum of this signal. So if this is the magnitude axis, C sub n absolute value, and this is the frequency axis in hertz. Now the fundamental harmonic have a frequency of 0.5 hertz, second harmonic of 1 hertz frequency, third of 1.5, fourth of 2, fifth of 2.5, and so on. Now I'm not going to substitute n values in formula of C sub n we obtained earlier. You do these calculations. I just don't care for these values. So let's assume that at 0.5 we have this magnitude, at 1 we have this, 1.5 this, and 2 we have this, and so on. So you get this when n equals 1, you get this when n equals 2, you get this when n equals 3, and 4, and so on. So what's going to happen if the period of the signal is 4 seconds instead of 2 seconds? So let's make this 4 seconds. Now the shape and dimensions of this pulse are going to be kept constant. So it still starts from -0.5 and ends at t equals +0.5. Only the duration of these zeros is going to be extended such that the period is 4 seconds instead of 2. So when we calculate C sub n, we still have to integrate from -0.5 to +0.5, since f of t is 0 outside this interval. However, capital T is now 4 seconds instead of 2, and fundamental frequency is now 0.25 hertz instead of 0.5 hertz. So let's see the effect of this extension of period of the signal on the spectrum. So this is the new spectrum. Now the fundamental frequency is now 0.25 hertz, and the second harmonic is 0.5, third is 0.75, and the fourth is 1 hertz, fifth is 1.25 hertz, sixth is 1.5 hertz, and so on. So let's just assume these magnitudes. Okay. Now let's just write down the notes about the new spectrum. So we can see that the fundamental frequency is going down. It was 0.5 hertz and now 0.25 hertz. We can also see that magnitude of harmonics is going down. For example, if you want to find the magnitude of a component that has a frequency of 25 hertz, you need to substitute n equals 100. Since this, you get this when n equals 1, so you substitute n equals 100 to get the magnitude of component that has 25 hertz frequency. Well, in this spectrum, to find the magnitude of this component, you need to substitute n equals 50. And it's pretty much obvious that C sub n is reversely proportional to the index of harmonics. So we say that the magnitude of components is going down in the new spectrum that is related to the signal having an extended period of time. The other fact is that the density of the spectrum is going higher. And by density of spectrum, I mean the number of harmonics in a certain bandwidth. For example, from 0 Hz to 1 Hz, so this is a 1 Hz bandwidth, it has two harmonics in the spectrum. While in this spectrum, each 1 Hz bandwidth have 4 harmonics. So the density of the spectrum is going higher as the period of the signal is increasing. Now, what about if t is to be 1000 seconds? What's going to happen? Fundamental frequency will be equals to 1 millihertz only. The magnitude of harmonics will drop down to 0.001 possibly, since the normalization factor of 1 over t equals to 0.001. The spectrum will look like this. So if this is 0 Hz and this is 1 Hz, fundamental frequency of 1 millihertz, second of 2 millihertz, and so on. The density of this spectrum is very, very high. It will contain 1000 harmonics within this bandwidth from 0 Hz to 1 Hz only. And the magnitude will drop to 0.001 at 1 Hz only. Now, we can imagine what's going to happen if t will approach infinity. The fundamental frequency will be very, very small that approaches 0. Now, it will not be exactly 0, since 0 is strictly reserved for the DC level. Let's say it's a very small frequency, let's call it df hertz. The magnitude of these components will be very, very small. It approaches 0, and the density of this spectrum will approaches infinity, will contain infinite number of harmonics in just any bandwidth. Now, if the spectrum has a density of infinity, what does this mean? This means that the spectrum have a components that works in each and every single frequency you can imagine, just any possible frequency, say 1.52891 Hertz or 1.612 Hertz, just any possible frequency. Why? Because if the fundamental frequency is df Hertz, which is very small, let's say this is 0 Hertz, as a frequency axis. So if until you reach 3 Hertz, that means that you have already covered all possible frequencies between 0 and 3. If we say that the first harmonic have frequency of df Hertz, the second harmonic have frequency of 2df Hertz, third harmonic have frequency of 3df Hertz, and so on. Now, what's the index of the component that has a frequency of 3 Hertz? So we have nf0 equals to 3 Hertz. f0 is a very small number. We agreed to call it df. So equals 3. This means that n equals 3 over df. 3 over df. So we say the 3 Hertz component is the 3 over df harmonic. Now 3 over df is a very large number, since df approaches 0. So if you move from 0 Hz to another frequency like 3 Hz, for example, in such a small step like df Hertz, you're going to cover all the points in between. So we say that the spectrum of non-periodic functions is continuous rather than being discrete. Also see that talking about harmonics in the context of Fourier transform is pretty much trivial, so we are going to avoid talking about it anymore. So harmonics are strictly reserved for Fourier series. Okay, so similarly for any non-periodic function, say a2 minus absolute value of t, we can imagine that it is a periodic signal that has a duration of infinity. So capital T approaches infinity. So we are going to derive the formula of the forward Fourier transform by taking the limit as t approaches infinity for c sub n from Fourier series. So we have limit t approaches infinity for 1 over time, integration over time, f of t a2 minus j 2 pi and f naught t dt. Now f naught equals to 1 over t, and as t approaches infinity, we have n f naught would be a very small number, let's call it df hertz. So n f naught equals to n df. Now I'm going to replace n df by a continuous variable, let's say f. Now f, if this is the frequency axis of the spectrum, f is a continuous variable such that it can take any value, any frequency. So we don't have any more functions of multiples of fundamental frequency f naught. We just have f of f. So if this is f of f, this is going to handle the density and harmonic index issues that I raised earlier. So no more harmonic index functions. You don't need to substitute the harmonic index to get the magnitude of the nf0 frequency component. For example, substituting n equal 4 to get the value of the 2 Hz component, or n equal 50 to get the value of the 25 Hz component, or even substituting n equal 3 over df to get the 3 Hz component magnitude. Actually, 3 over df is such a large number. Let's say, for example, 3 trillions. So if you substitute n equal 3 trillions and multiply it by 1 in a trillion, you will get 3. So you just substitute f equal 3 in f of f. What about this particular, replacing n, a discrete variable, by a continuous variable like f, can be found in my video about integration. You can check out the link in the description section. Now, by integrating over a single period of time, so from minus t over 2 to plus t over 2, for example, and as t approaches infinity, let's say that f of f equals to limit as t approaches infinity for 1 over time integration from minus infinity to plus infinity for f of t e2 minus j 2 pi ft dt. Now, as for this part of 1 over t as limit t approaches infinity, it will be a very small number such that when it's multiplied by the value of this integration, it will make it 0. So if this integration gave you this function, then the multiplication by the stupid factor of 1 over t as limit t approaches infinity will make this look like this. 0 everywhere, regardless of the value of the function. Since if this magnitude is multiplied by 1 over t as t approaches infinity, will give you 0, and this will be 0, and this will be 0, and so on. Now, it is true that the magnitudes of these components are approaching 0. However, we can analyze such a signal. So it's very convenient for the moment to neglect this factor. So we say f of f equals to integration from minus infinity to infinity for f of t to minus j 2 pi f t dt. But you can keep in mind that this magnitude is not real because it is not scaled properly, since we have neglected the normalizing factor to avoid corrupting the signal. We will talk more about the consequences of neglecting this factor when we derive the formula of the inverse Fourier transform. Now, in Fourier series, we used to synthesize the harmonics to get back the original time domain function using this formula. F of t equals to summation from n equals minus infinity to plus infinity c sub n e to plus j 2 pi n f naught t. But now we have, instead of c sub n, we have f of f, and instead of n f naught, we have f. And we need to replace this summation by integration from minus infinity to plus infinity. Now, I have talked about this particular extensively in my video, what does the integration mean. So if you want more details, you can check the video right now. The link is available in the description of this video. So we have f of t equals to integration from minus infinity to plus infinity f of f e to plus j 2 pi ft. If you remember the 1 over t normalization factor that we have neglected in the Fourier transform and said that f of f is not properly scaled so that the values are not actually true. So we're gonna scale them right now. 1 over t equals to f naught, which equals to df. So we're going to multiply this integration by df such that f of f is scaled properly, such that we recover f of t correctly. Now, to elaborate what's happening, just forget about Fourier transform for a moment. The formulas of the Fourier series were as follows: c sub n equals to 1 over time integration over time f of t e to minus j 2 pi n f naught t dt, and f of t equals to summation c sub n e to plus j 2 pi n f naught t. Now one may rewrite these formulas as follows. You say c sub n equals to integration over time f of t e to minus j 2 pi n f naught t. So he just neglected this normalization factor. So the spectrum he will get is not scaled properly. He just take care of the issue when he synthesized the harmonics to get back the original time domain function. So you can see here this normalization factor that was placed in the inverse formula. So this is absolutely true, and this is exactly what happened when we wrote the formula of the inverse Fourier transform. This actually also happens in the formulas of the fast Fourier transform. We talk about them later as well. Now let's see how does the IFT works, the inverse Fourier transform. If we have an even function f of t, which is an even function, what does that implies? That means that the Fourier transform of f of t is a real function, since the spectrum doesn't contain any sinusoidal components. So the Fourier transform, which is f of t e to minus j 2 pi f t dt, can be simplified into integration from minus infinity to infinity f of t cosine 2 pi f t dt, since integration from minus infinity to infinity f of t sine 2 pi f t dt equals 0. So the spectrum of f of t doesn't contain any sinusoidal components. So we can simplify the Fourier transform to this formula. This gives us f of f, which is a real function. Now I have intentionally chosen an even signal for simplicity. So assume f of t is an even function, which is a voltage across these two nodes. Now Fourier transform analyze this signal into a sum of infinite number of sinusoidal sources. So let's assume this is a cosine 2 pi f1t, and this one b cosine 2 pi f2t, c cosine 2 pi f3t, and so on. So if this is the frequency axis in hertz, and this is the time axis in seconds, and this is the magnitude axis. Now this is the magnitude of the frequency component, not the time domain signal. So you need to take care of that. So if this is the spectrum of f of t, then let's call this plane of this plot f of f. This is a magnitude axis and this is a frequency axis. So f of f gives you the relation between the frequencies and the magnitude. So these are the magnitudes and these are the frequencies. So f of f give you the relation between f and magnitude. So for example, if you substitute f1, then you get the magnitude at this frequency, which is a. And you substitute f2, you get its magnitude, which is b, and so on. What's going to happen when t equals 0? When t equals 0, cosine 2 pi f1t will be equals to 1. Cosine 2 pi f2t will be equals to 1 as well. Actually, all the cosinusoids will be equal to 1 when t equals 0, regardless of their frequencies. That means that these sinusoidal sources are giving you a magnitude, a voltage equals to their magnitudes when t equals 0. So to find f of 0 in time domain, you just need to sum up all these magnitudes. This is only valid if t equals 0. So we're going to find this area in the frequency domain to sum up all these magnitudes. And what do we get if this is time domain? Now this is the magnitude of the time domain signal. Okay, so the area under f of f in the frequency domain equals to the value of the time domain signal when t equals 0. So this t equals 0, this is the value f of 0. So we have integration from minus infinity to infinity f of f df equals to f of 0 in time domain. So this area equals to this point. Now, what about f of 2 seconds? What's this equal to? F of 2 seconds in time domain, of course. So let's see how do these frequencies run over time. So this is the DC level running over time, so it doesn't change. This is f1 Hertz frequency component running over time with its corresponding value, magnitude. And this is f2 running over time. Of course, f2 is higher than f1, and so on. Now, when t equals 2 seconds, the f1 Hertz component have done, let's say, 5 cycles after 2 seconds. The other f2 Hertz component have done 2.518 cycle, and so on. Each single frequency component has done different number of cycles. So it became just a mess. Now the good news is that we know the equation of each single curve thus. To characterize a sinusoidal, all you need is a magnitude and a frequency. And we have both of them. We have the frequency of each single one of them, and we have the magnitude of each single one of them as well. So we know that the equation of this curve is b cosine 2 pi f1t, and this one has this equation, and so on. So all that we need to do is substitute t equals 2 seconds to find the value of each curve at t equal 2. So we will multiply f of f by cosine 2 pi ft. So let's substitute f 2 seconds. So we have f of f times cosine 2 pi f times 2. Let's just keep f variable such that every magnitude is being multiplied by its corresponding sinusoid with the same frequency, which gives you the value of each source thus. Now all you need to do is to integrate this from minus infinity to plus infinity to sum up all these points, and you get f of 2 seconds. So we have, when t equals 2, we have some magnitude, say this f of 2 seconds in time domain. Now, if you check the formula of the inverse Fourier transform, which was f of t equals to integration from minus infinity to infinity, f of f e2 plus j2 pi f t dt, you will find that this formula we got earlier is just a copy of this one with substituting t equals 2 seconds. So f of 2 seconds equals to integration f of f e to plus j 2 pi f times 2 df. We can say this is valid as well for any other point, say t naught. There is another interpretation of this. Actual multiplication of f of f by e to plus j 2 pi f t naught gives you the spectrum of f of t minus t naught in the time domain. And integrating the area, finding the area under the spectrum gives you the value when t equals 0, so this gives you f of t naught again. Okay, that's all I have for the moment. I know you have tons of queries, questions, notes about this video. It's a very interesting subject and it has a tremendous amount of applications. So just leave the questions in the comment section and I'll answer all of them. If you have any suggestions about next subjects and videos, just leave it in the comments as well, and thanks for watching.